Now I'm going to derive the Lorentz transformation for distance and length from the length contraction as L naught square root 1 minus v squared over c squared equals L. Okay? How we're going to do this is we're going to start with the Galilean transformation, which just means changing, transformation just means changing measurements from one reference frame to another. Let's start with this. Let's say we have two reference frames, like this. We'll call this the not prime frame and this the prime frame. Prime frame traveling at velocity v with a little person over here, and not prime frame with a little person over here. And we say that there's an event over here. Move it over a little bit. An event over here that's also stationary. So the not prime frame and the event are stationary, so they're said to be in the same reference frame. While this reference frame, the prime frame, is moving. Okay? So this is right now this is at time t, or time t prime equals 0. They are in a superposition, they're in the same place, okay? And now in a later time, when time has passed, they're going to be in these positions. This is the not prime frame with our little person. And this is our primed frame with our person. Prime traveling at velocity v, okay? Now, they're going to have their own measurements. This person is going to measure distance as x and time as t, and this person is going to measure distance as x prime and time as t prime. And the prime just denotes measurements from different reference frames. It's not anything special. It's just this is the distance measured from the origin, from where this person is, in this reference frame, and this is the distance measured from the origin in this person's reference frame. Now, in a Galilean transformation, it's classical mechanics, so t equals t prime is just time. And this isn't the case in special relativity, but just for this purpose, this is going to be the case. Okay. So, we say that the distance from the origin that the not prime person measured this event to be is going to be represented as x. The distance this person in the prime frame measures it to be from their reference frame is x prime, okay? The distance the non-prime person is going to measure the prime person to have traveled. It's going to be the velocity of this reference frame multiplied by time, t, and this person is going to think that they've traveled, since it started, the velocity times t prime. Make sense? Okay. Now, just a little bit of mathematical relationships between this. We can say that x equals, so x in the non-prime reference frame equals some measurement in the prime reference frame, which would be x prime plus vt prime. We see that? X prime plus vt prime will give us x. We can also say that x prime equals x minus vt. This is going from measurements of x and t to measurement of x prime. This is going from measurements from x prime and t prime to measurements of x. Again, x prime equals x minus vt. Easily enough. That's what this person sees, that's what this person sees. Okay. Now for the relativistic part. Just keep those equations in your mind. I'll write them down here. So we say x equals x prime plus vt prime, and x prime equals x minus vt. Okay? So, let's say that this distance x is the real distance from the origin to the event is L naught, right? So let's plug that into the equation. X square root 1 minus v squared over c squared equals something. Now again, what L naught is it's the length or distance of something in its own reference frame. What L is it's the length or distance as observed by somebody in another reference frame whose difference in velocity is v. So we can say that x is the real distance from in the not prime frame will equal the distance that the prime frame observes it to be. So x times the square root of 1 minus v squared of c squared will equal the distance that the prime frame thinks it is, and the person in the prime frame will say that the distance is x prime plus vt prime. X prime, vt prime. That's what they're going to say this distance is, right? Makes sense. So we just rearrange this. We say that x equals x prime plus vt prime over the square root of 1 minus v squared over c squared. Just plugging into the length contraction, because x prime plus vt prime is replacing L. That's the length that is observed by the other reference frame compared to the real length x as L naught in its own reference frame. And this is one form of the Lorentz transformations. And this is converting, if you have measurements in x prime and t prime, to measurements in x. Now, if we wanted to switch it, what we can do is we can just say x prime equals, we turn the velocity negative, because from this person's perspective, this and this are just going in a negative velocity, so it would equal x minus vt over the square root of 1 minus v squared over c squared. Oops. I'm gonna prove that for you now, though. Anyway, I'm just explaining that's the logic behind it. You can just reverse the velocity. But let's do it now anyway. So let's say that x prime is now L naught, and you might originally think, wow, this doesn't make sense. Like, how can that be? Let's imagine that there's like a ruler in the prime reference frame. Okay. And later on, at a later time, when this reference frame is moved to here, the prime reference frame is moved to here, this ruler is still going to be here. This length is still going to be here. What's being looked at now is not the actual position, but actually the length. The length from this person in their origin to where this is positioned in terms of x away from them will be that actual length will still be moving with them. It's a length that's measured in their own reference frame. So it's L naught. Like in this situation, when the vent's over here, the not prime frame is over here, the prime frame is over here, this length will still be with them, still be moving. It'll just be a measurement in their own reference frame. Alright? So if we understand that and we plug that in, we say x prime square root 1 minus v squared over c squared. This length that is measured by this person, the prime reference frame, times the square root of 1 minus v squared of c squared, is going to equal the length that a person in the other reference frame, whereby the difference between the frames of the velocity v, it's going to be the length that is going to equal the length that that person perceives it to be, which will be x minus vt. This will be the length, because x minus vt is going to replace L, that this person perceives that length to be. And this will be the actual length that it's measured in its own reference frame, such that x prime equals x minus vt over the square root of 1 minus v squared over c squared. And this is the Lorentz transformation for length. If there's a measurement being made through a time interval t in a motion, this is the case. Again, if you're converting from x and t to x prime, we have over here x equals x prime minus vt prime over the square root of 1 minus v squared over c squared. For our other version, this is the main version though that you'll see, and we see that if this is made in a interval of 0 time, then this value goes away, and it just reduces back to the length contraction. And so this is a very good idea in special relativity, and I will derive it for you in another video, again using more mathematics than just this. Sometimes you might also see it like this: x prime equals x minus vt times gamma, just because 1 over the square root of 1 minus v squared of c squared is gamma. And this is the Lorentz transformation for length and distance. And in my next video, I will do the Lorentz transformation for time.